Hello, everybody, all three of you, and whoever is joining online. My name is Berzan Gashi. I am a postdoc at the Fraunhofer Institute for Applied Solid-State Physics. I did my PhD here at Uni Freiburg, and now I'm helping out a little bit with some of the lectures for Professor Kwai. Today we're going to talk about antennas, and in the middle of the talk we're going to have also a small demonstration on a simulation tool that you use nowadays in modern times to design antennas. And then we will conclude the lecture. It's more of an introductory lecture, nothing really complicated, nothing really, hopefully nothing too boring. Let's start with the concept. What is at all an antenna? Well, an antenna is a device that enables the conversion of electromagnetic waves from free space towards a bound medium, something like a microstrip line, a coplanar line, whatever you need, a metallic conductor. Nowadays, we make use of antennas in multi forms and multi ways. I mean, usually when you think of an antenna, you imagine a Yagi-Uda antenna, which you used to have previously for TV reception, or something like Cassegrain antenna for satellite reception. But nowadays, antennas are very minuscule and integrated in most any device that we use that has any wireless functionality, also Bluetooth functionality. Usually the antennas that we come in most contact with are those in our phone, as seen to the right. This is an example of one such antenna on iPhone 4. Obviously, these have been more modernized and upgraded in the recent years. We will start with a bit of an introduction, what types of antennas there are at all, and then we'll move to a bit more of an example of a modern antenna, and then, as I said, a bit to CSD as examples for how to design nowadays modern antennas. Well, the most simple form of antennas and the most ancient form of antennas are wire antennas, like dipoles, loops, and helical antennas. This you've probably seen mostly, and I mean, upgrade to these are also like the Yagi-Uda antennas, as such, for the reception of TV information. But these are the initial antennas that were developed to test at all the transfer and reception of electromagnetic waves, and to even in the times of to even identify at all if EM waves are capable to travel through a medium without vacuum, without air, and so forth. Another type of antenna, which is usually mainly used nowadays as well in military purposes, but also in scientific purposes when designing low noise amplifiers that are supposed to receive radiation from space. Usually you have a horn type of antenna transition as it gives you the most directivity gain, and it can be easily integrated in a packaging for a split blocking module. So basically, you can imagine a chip which is integrated into this packaging. The packaging consists of a metallic alloy that has these cavities inside of it drilled, and these cavities are equivalent to a waveguide, and then this waveguide opens up to form either a pyramidal horn, a conical horn, or a normal waveguide transition. Usually these are also used in RF, also for testing, for characterization of other antennas as well in the lab, very frequent use. Modernly, what antennas are nowadays mostly made of are these planar solutions, so microstrip antennas, and a circular in any shape, type, or form. You have a dielectric. Over the dielectric, you process a certain metallic layer, and that metallic layer can then be used to excite EM waves, which or fringing fields that are capable to radiate out to free space. In this form, you can form arrays, which are basically a bundle of these antennas, and make use of the multiplication principle that the system's behavior will be equal to a unitary antenna multiplied by the system's characteristics. So you can make use of defined distances to add up the respective radiation patterns, so that you have a combined radiation pattern of the complete antenna setup of these multiple antennas. In order to increase directivity and in order to increase reachability, you can obviously use a lens. A lens, what it does, technically, it takes a certain radiation. It has a focal point. It takes a certain radiation and delays it into a delays parts of the radiation into such that the wave that exits the lens is a planar wave, usually. And you can also use a Cassegrain antenna, which builds up on the concept of parabolic reflectors to either transform an EM wave from a plane wave into a directed wave or direct it into a plane wave. How the waves travel, how one can imagine the excitation of the current to be is if you look into the left, you see that there are two wires. These two wires are being driven by a differential signal. Mainly, the current goes in one direction on the upper wire, in the other direction in the lower wire. This causes certain current amplitudes to voltage amplitudes to be generated, current amplitudes to be generated in along the wire and along the length of the wire in terms of a certain wavelength. And usually for every lambda half, you'll have a crescent, and then at the other direction, you'll have a peak. If these EM waves, if these current waves see an interrupt, which is either the end of such a wire, or either if you try to bend the wire, then they will part of that wave will reflect back to where you incited it, and part of it will be radiated out. And that part which is radiated out, you can obviously control by controlling the shape of the interrupt, whether it's a stub here or whether it's two openings. And these openings also dictate how these radiated waves, whether they will be in phase or out of phase. And if they're in phase, they will obviously have a constructive interference. If they're out of phase, they have destructive interference, generating different shapes of the radiation patterns. As you can see here in the middle, the size or the length of the interrupt really matters in terms of how the antenna will radiate out, and how these shapes will look like. How these shapes then are generated, whether it's one main coil or whether it's two secondary coils generated, depends on the length of the interrupt. And often enough, it's rule of thumb is to take lambda a half for a length. The respective components of an antenna are that it has a near field, a reactive near field, which is either reactive or radiative, and then a far field component. The near field component is something that we won't be discussing, as it is not used in the devices such as communication for wireless communication or radar in the subject of in our subject, in our case here, more for NFC communication, which is not the subject of this matter. The most important property is, as I said, not the near field which is the reactive and the radiative near field, but rather the far field. In the far field, the antennas have already the radiated EM waves have already entered a plane wave mode and travel through free space. Where that distance is, if I have one transmitter, and where that distance is with respect to where the near field, the reactive near field, the radiative near field, and where my far field is, depends on the size of my antenna. And the size of my antenna, as we saw before, depends on what type of radiation do I want to achieve, and what type of radiation at what frequency do I want to achieve that radiation. So the most important component is that L, the length of the largest dimension of the antenna, which defines then at what point the far field will be. If we're going to measure an antenna which operates at 2 gigahertz, we would probably have to go outside of this room to be able to reach the far field. If we are measuring an antenna which operates at 400 gigahertz, you will just move 20 centimeters away and you'll be at the far field of it. The formulations, you don't really have to remember. What you have to just know about is the concept that the far field exists, and that there's major parameters such as the theta and the azimuth. What does the theta and the azimuth say? If I am the transmitting antenna, this is my theta and this is my azimuth. My theta defines my elevation, where my beam is looking at, and my azimuth defines where the orientation of that beam will be. For example, if I say, okay, my azimuth is 90 degrees and my theta is 45 degrees, then my beam is looking in this direction. But if I leave my 45 degrees theta, my elevation, how long this from my head to my arm, the angle is. If I say, okay, I want to move and look at the door right now, which is 180 degrees from my right hip, then I would have to have an azimuth of 180 degrees, and I would be looking at that. And if I was at 270 degrees, I would be looking in this way, and so forth. And this way, you can characterize with these two parameters. You can characterize where your antenna is looking. Because if you have an antenna, you want to sell it to somebody. You've designed your own antenna. You want to sell it as a product to a customer. Then the customer will ask you, well, what does the antenna do? So how much does it accept power, and where does it radiate the power out to? And then you do a characterization of antenna, meaning that you take a turntable and you try to do these half circles over it, and you try to characterize every side of these half circles. And when you try to represent it to the customer and say, hey, this is my antenna that I designed, and these are the results, the customer has to be able to know in which direction, what are these results telling you? Because you can say, okay, I have in my E field, I have 5 dB gain, but in what direction is that E field? And is it in what azimuth and what elevation is it oriented? So these are parameters that help us to define then this far field. Other principles of antennas are directivity. As said, then the antenna is not only capable to take energy bounded to a conductor and radiate it out into free space, it is also able to direct that energy into a certain direction, and that directed energy, that is called the directivity. The directivity is basically the power per solid angle in terms of this is like in terms of a sphere, of a isotropic radiator. That's why the 4 pi, and the total radiated power. Yeah.
Is it the direction of the EMF that we are transmitting, or like what is the direction?
Yeah, it is basically the direction of what you are defining as this is the EM wave that I'm talking about. This is the direction of the radiation that I'm talking about. It could be your main coil, it could be a side coil, it could be whatever. Usually you talk about the main coil only, but if you need to define other parts, I mean, the antenna radiates in all directions. Usually if it has a metal ground plane underneath, it will radiate upwards only, but when it radiates upwards, it radiates over 180 degrees. You have side coils, you have all possible radiation patterns. And with the phi and theta, you use to define, to basically in that sphere, to move in that with those spheric coordinate system, to move and say in what direction am I referring to which cut of the far field plane.
And then the direction selectivity is selected by the bending of the coil, the T that in the previous slides, the T that yeah, in the next previous one.
In the previous one.
So is this directionality caused by
No, the T is basically the period. The T is the time it takes for the current to move to the edge of the conductor and to see the interrupt. And usually the T, you can either define it into electrical length or in time. Electrical length is basically the lambda half of an electrical length to the conductor. That's at the point where it basically is the amount of time that it takes for the current density in the conductor to be maximum and minimum. So basically you have a one full wavelength. You went from your sinusoid, you have a sinusoid excitation, so you went from one crescent up to the one crescent down, and you made your full your full period, and then you move to the next period. And for every full period that you move, in the positive period you have a positive current running through, so you generate EM waves, and then in the negative period you generate a negative current flowing through the conductor, which means by the time your EM waves have moved here, you've created some, they've traveled already the T time, so you've waited a quarter of a period. That has taken some time to generate they have had positive current, which has moved from here, this side to this side. You've generated EM waves, they move outwards, and then you have a negative current exciting in the conductor. Basically, you're generating EM waves on the opposite side, meaning that you would have to cancel out what is present here, but because there's nothing present here, because there's been a time passing, the EM waves have traveled around, you'll get a addition of these waves that you've generated, and you basically get this kind of shape that creates the radiation pattern then. So this rounded shape, because what is in the beginning is canceling out your radiation, but what is outside has already been transmitted. That's why you have this like expanded, and then you have this coming into the transmitter, and this happens all the time, because all the time the electrons are being shifted to this side, and then this side, and 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 this you can look at it as either an electrical length moving within the conductor, or you can time it as a period, certain nanoseconds, how the shift of these occurs. But this is bound to what the interrupt is, how much the length of the interrupt is, and the length of the interrupt then defines what type of radiation you have, and what type of radiation you will need in terms of, well, do I have an antenna that works at 10 gigahertz? Do I have an antenna that works at 20 gigahertz? Do I have an antenna that works at 2 gigahertz? And if it works at 2 gigahertz, these wires are going to be far longer than if it works at 10 gigahertz or at 20 gigahertz, or at 300 gigahertz. You will have to process them in a semiconductor integrated circuit processing technology, integrated in the chip, so it'll be minuscule, it'll be micrometers in size. We'll see an example of that, and we'll see a visualization of these things via CST. It will help, probably. Some parameters, as I said, directivity. An antenna is not only able to radiate the signal anywhere, it also can be focused to a certain direction. And this directivity, you always, the parameters of an antenna, you always define with respect to an isotropic radiator. So with respect to something that radiates on all sides equally. So always with respect to that one, what is my directivity? That's why it's always an I in the end. When you tell an antenna gain, you say, oh, it has 20 dBi, because it is with respect to an isotropic radiator. You always have to take something as a reference. Obviously, you have an antenna gain as well. The antenna gain, well, you can define it in dB and with 10 log 10, as all of you probably know. And what is the gain? The gain is basically the multiplication of the directivity with the efficiency. And the gain is the realized directivity. Realized directivity, it sounds stupid, but it is basically what is really is radiated out with the losses that are incurred in the near field, in the not near field the same, but in the conductor itself, in the substrate and so forth of the antenna. And that efficiency is defined as the radiated power versus the input power. And the input power is basically the power that you drive into the antenna, ignoring any possible reflection or something like that. This is how a pattern looks like. And in this, basically our demonstration, how you would represent an antenna pattern, a far field pattern, you would represent in this polar plot with degrees determining where your azimuth is, where your elevation is, depends on what. Usually you would give a certain, for these cuts, you see this is a 2-dimensional cut. The antenna radiates in 3 dimensions, and usually you have this elevation. So here you have the elevation cut. What we see here is basically an antenna which you're seeing all this plane of the antenna, but you don't really know. In this case, is it this plane, or is it this plane, or is it this plane, or is it this plane? Because it's not given here. But in a proper polar plot, you would have, yes, this side always a 2D cut. My antenna is radiating in all 3 dimensions, but I'm only able to plot one cut. And then if I plot, for example, this cut, this side here, I would have to tell the reader, okay, this cut, yes, but the for this cut, first of all, you will have an azimuth of 90, and then the elevation till 90, and then an azimuth of 27, and then the elevation till 90. No, 0 to 90. So you would have to redefine or rewrite this plot. But basically, this is how a polar plot looks like. You have an amplitude on the horizontal axis. You have the amplitude, and on the radial axis, you have the degrees with respect to where the elevation is. And when you define an antenna, you will usually see the direction. This is called the main coil. The main coil has the properties, it has a direction. And usually when you make an antenna, you would like the antenna to look upwards directly or to look. Antennas can be something that shoots upwards, something that shoots downwards, something that shoots isotropically, something that shoots end fire. You call it when it shoots perpendicular to parallel to the substrate. Usually it has a main direction. This main direction is taken as a main coil, and that main coil is basically what we see here, this extended part. And the main coil has a main coil direction, either at 0 degrees or shifted. You would tendentially have it at 0 degrees. And beyond the main coil direction, it has also a 3 dB point. So the point at which there's a half a drop of the transferred energy, and that point is called then the width, the main coil width. You take that as the width of your main coil to define, for example, okay, my antenna has a certain gain, it has a certain directivity because of the physical properties. I know the losses, from that I can get the gain, and I characterize now the gain, and I can say, okay, the gain of the antenna is in this coil, and in that coil it has a 3 dB beam width of whatever, and the 3 dB beam width just is a parameter to characterize antennas, because people will ask you, okay, how much gain does it have? What is the 3 dB beam width? Because they want to know how big this coil is, and they will ask you the direction, what the direction of the coil is, and you have to say, okay, it's at 0 degrees, the beam width is 10 degrees, so then they know, okay, what type of receiver to construct. Another important parameter is the side lobes. Why are side lobes bad? Because when I'm trying to send you a photo, I want to send it to you. I don't want to send it to him or to her or to whomever. And if I have an antenna which has gigantic side lobes, I will send the information to you, and at the same time, him, her, and everybody else would receive it. Obviously, in phones, that's something else. We work with pre-packages and encoding and blah, 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 because we're anyway radiating everywhere. But if we were to have an unencrypted channel and we only were directing our information, then side lobes are very bad. So you would require a reduced side lobe level. Another important parameter is the aperture. So basically, an antenna not only has the parameters such as like gain, directivity, and so forth, but it also has an aperture, which is like the physical. It either can be a physical aperture. You can either have a gigantic antenna that you design to have a very focused beam. So what does a big antenna? The bigger the antenna, the more focused the beam becomes. And if you want to receive, for example, the radiation that we receive from space, we technically receive a lot of low energy radiation. In order to increase the gain on that, and to be able to even see something from passive black bodies radiating from space, you make a gigantic antenna to accumulate as much as possible, to have as much as possible of an aperture, so you have as much as possible of a gain. And this aperture, this lateral resolution, can either be obtained by increasing the size. This numerical aperture can be either by increasing the size, or it can be also done by making a multiple arrays. So instead of having a very large antenna, you have multiple arrays of that antenna. That we will come back again to that part. What is important to also say is that, okay, you can look at the antenna as a radiator, but you can look at it as also a simple circuit. This is a simple electromagnetic circuit. And what is the antenna in basically in the case when it is transmitting, and in the case when it is receiving? Well, it is a single port device. It's a one port device. If it has multiple antennas, if you're designing an 8 by 1 antenna array, then it is an 8 port device. So per antenna input that you have, you will have a 1 port device. If you have one antenna which splits then the signal to multiple antennas, it will still be a 1 port device. But if you have an antenna array with individual sources, then that will be an 8 port device. But here we have only 1 port device. We're only talking about one sender. And in terms of the sending part, when it is in transmitting mode and receiving mode, when it is in transmitting mode, you can see that it consists of basically you can approximate it, that it consists of a loss resistance, of a radiation resistance, of an internal voltage source, and a reactance X. Or you can look at it on the admittance side and say just basically in terms of, and either define a voltage source or you define a current source. It's anyway equivalent. In terms of the transmitting side, you can see that the voltage will be, this V0 will be 0 because you don't have anything receiving, you're transmitting. The V0 will be at some value if you're receiving EM waves from outside. You're now transmitting, which means you have a Vn, which is defined a voltage swing, a sinusoidal voltage swing, whatever the case. Part of your energy that you put into the antenna, depending on how good you're matched with the antenna, because the antenna is a single port, so you come with a load on it. And when you come with a load on it, you will have to have a transformation, because you will have an antenna which is a 50 ohm, and then come with a load with an active device, and the active device has a load of 37 plus 15J or something like that ohm. And this load will always vary because the active device does change the S to 2 due to depending on the state of compression it is in, and with a frequency neutral. So you have something that is a variable load, you connect it to your antenna. You will obviously not have an antenna which everywhere radiates perfectly. So you have an antenna which part of the energy it will not accept at all, to reflect it back, part of energy it will accept, and part of the energy will simply be lost in the conductor itself. And this simply lost part is it can be approximated by the loss resistance, and the part that is radiated out can be approximated by the radiation resistance. Just to have in mind that this can also be, an antenna can be represented by simply one port device, a one port circuit. In the case of the reception, obviously you will have a voltage source which is not 0, but you have a voltage source which is higher because you're receiving a signal, and then it refers to each other. So it's very, very, very simple in that sense. Now we talk a lot about like antenna types and some of the parameters. As parameters, we began with antenna types. We had wire antennas, the dipole, the circular antenna, the helical antennas, horn antennas, which were basically used previously a lot in military, then now in research and then space-related subjects. We talked about more modern antennas, microstrip line, and the options of increasing the directivity and gain of these microstrip line antennas using Cassegrain implementations, array implementations, lens implementations, basically lenses which are used with these antennas. And now we'll move a bit more to the modern types of antennas. So what currently is being done, because what currently the research is significant in antennas is in the antennas that are integrated within chips, within MMICs, within monolithically integrated chips, and in microwave, in millimeter wave and sub-millimeter wave range. And these antennas, as I said, can be either radiating upwards, they can be either radiating downwards, and for that downwards radiation you need a flip chip process. What is a flip chip process? Basically is the ability to have an MMIC chip to be able to flip it on a carrier, and that carrier to be able to provide the respective signals that you need for it to function. And your antenna is not radiating where the processed metals is, so it's not radiating on the upward side, but it is radiating on through the substrate on downwards, and that's why you flip it to be able to have it radiating on the upward side. The benefits of that are because you have a dielectric which is very high in epsilon r, which is a high dielectric constant, and usually if you have a device that has a high dielectric constant, the EM waves will not want to permeate into free space, so they will want to resonate within the dielectric block that you have, and you don't want that. You want an antenna that sends and receives things, not that keeps makes a dielectric resonator. Another way is to shoot with a Vivaldi antenna, to shoot end fire, to shoot parallel to your substrate, but Vivaldi antennas find less and less use due to the fact that they are quite big in size. And we are talking here about devices that are in the range of 50 to 100 micrometers for the processed, for the metal part. Very small. So this is an example of one such antenna. So it's a patch antenna, which is processed on a MHEMT, InGaAs, MHEMT, MIC process. So you probably know InGaAs and you probably know metamorphic HEMTs. Metamorphic HEMTs are like HEMTs. HEMTs are field effect transistors. In what makes it metamorphic is that there's a transition layer for such that the transition layer such that the mesa or the AP is better adjusted to the substrate, to the gallium arsenide substrate. This is a process where the antenna is the process itself is, in this case, is irrelevant. What is relevant is the fact that this is a minuscule antenna. The dimensions are in the range of 50 to 100 micrometers. So 50 for the shorter edge, for the radiating edge, 100 meters for the 100 micrometers for the edge where the patch is fed. Usually you have a feeder. You have here is a transition from microstrip line to coplanar wave to microstrip line again. Why this was made this way is due to adjust the matching of the antenna. So it is the intent of having as much of the signal as that is fed here downwards to be able to enter this patch here and resonate. And how does this patch function? Well, there's an EM wave that travels through here. It excites a certain current, surface currents on top of the on the edge, and basically surface currents fluctuate from positive to negative, from positive to negative, from positive to negative with each traveling distance, and this traveling distance here is lambda half, and from that you're able to generate surface waves, and from the surface waves you're able to generate also evanescent waves, and these evanescent waves are the waves that are then have the capability to disperse into free space. Obviously, a lot of the energy goes also in the substrate inwards. That's why the substrate is also covered with a certain array structuring. Now, modern antennas are not just ending there. So you're not just making a metal and you're shipping it. Because they're so small, as I said, you need this numerical aperture, right? So if you want to look far away, you want to have a big ass antenna. And if you don't have that kind of antenna, you have a very small one, you have to try to increase this numerical aperture, or try to increase the gain, to try to increase the directivity. And for that, in this case, this antenna makes use of a dielectric resonator. So what does this antenna do? It takes the energy from the circuit, it radiates part of it out. Every antenna has an efficiency. As we said, a lot of the circuit is an active circuit, so it's switching its load always. And in a certain band, you're not masked very well. In a certain band, you're masked better, so you're taking more of the energy out. In certain bands, you're just reflecting it. That is being part of that is being radiated out into this quartz. This is a quartz monolith, a quartz dielectric resonator. Why is it called a dielectric resonator? Because of its size and of its geometrical size, it starts to resonate at certain frequencies if you have an excitation. So if you have an excitation, it starts to resonate, and it basically helps you into accumulating this radiated pattern and directing it towards free space in a more controlled manner. So you're radiating out whatever from the antenna, and through the quartz you're able to control it, to direct it a little bit, and then to represent it into a layer. And as we said in the beginning, an antenna needs an interrupt. It needs something it needs a dielectric interrupt, for example, from a conductor to free space. So it's an interruption of the conduction process. And here you have a dielectric element. So you need another interrupt. And for that interrupt, there's a thin layer of can be ceramic, can be diamond, whatever, which is a thin layer of transition that it causes this interrupt. For example, you have this wave that is resonating in this object, and then you have a certain interrupt to cause this effect of having something that radiates out. Because you always need an interrupt. In our normal life, it's usually a conductor and the air. The transition is the interrupt itself. But if you have a dielectric resonator, you don't have a conductor. You have something that has an epsilon dielectric constant of 5 or 6, whatever, or 8 if you take ceramic, and that requires a certain interrupt to be radiating out. And here, this interrupt is diamond, which is basically something with a higher electric constant. These things, as you can see, they can be integrated in these like microstrip, in these chips. And this is a transmitter at 400 gigahertz. This is like a multiplier taking the signal from around, I believe it's around 7 to 12 and multiplying it up to 400 gigahertz until here at this point. And all of this is designed with this chip integrated in it. So this is basically, the antennas are no more horns or no more gigantic things that are looking outside. Obviously, there's applications for that as well. But in the RF world, in the RF scientific world, they are minuscule solutions within the chip, because these minuscule solutions allow you to then multiply these antennas and put, because you're wanting to not have a gigantic antenna, but you want to have small antennas, multiple of small antennas, to be able to reconstruct a gigantic antenna. And these are processed in chips like these. So you design the chip, the active part, there's a multiplier, buffers in between that buffer the multiply signal. Every time you multiply a signal, you have a harmonic. The harmonic has less energy than the primary component of the signal, which means you need to buffer it, you need to increase the amplitude. And here you have like a step where you amplify it, you buffer it, you multiply it, you buffer it, you multiply it, you buffer it, and then you have another stage of multiplication, of buffering, of multiplication, and then an amplifier to be able to radiate out whatever the MET amplifier goes into the antenna, basically that antenna that's being seen there. And as I said in the beginning, these modern antennas, to be able to increase their gain, because they're so small, not only can you use the quartz and a diamond, whatever, you can also use a lens. And lenses are these polymer things that are you can do a 3D print. This is a 3D print, for example, a 3D sinter, but you can also carve in high density polyethylene, whatever, to create antennas as that. And then, yes, but obviously we saw how you can design how the antenna looks like. It's a one-port device. It's more complicated than what I showed there, but there's formulations to define what kind of radiation pattern you need. There's equations that you solve. Basically, forms that simplify the Maxwell's equations. That's what people did in the early 20th century. That's what people did all through until modern computers were developed and computers became available for research. And nowadays, what people do is they use electromagnetic simulators. So they use programs, and I'll show you one such program. They use programs that do electromagnetic simulations that basically solve these Maxwell's equations in terms of using finite element methods. So in basic sense, what they do is they take a grid. You define, depending on the frequency that you're operating in, you define a grid length. It's called a mesh. So you define a mesh density. And what does the mesh density do? The mesh density discretizes the whole space into small quadrants. And for that small quadrant, it solves the direction of the propagating electromagnetic wave in terms of the magnetic and the electric component. And for each of that, it defines a S-parameter matrix. And all these S-parameter matrices, it multiplies over and over and over and over in all these chunks to give you a final solution of where the spread of the electromagnetic wave is from the source that you inside. This is very cumbersome if you're doing it per hand, maybe at some point impossible, but it is very easy if you do it using electromagnetic simulator, or easier. And for that, we will go to this slide, and this slide tells us to go to the CST demonstration. So we'll go to the CST demonstration. Okay, so let me just log in. Okay. And actually, let me get a mouse. It's definitely better. So, I hope it can be seen. I hope it's being recorded. So what is this? Well, let's start with this program is called CST, Computer Simulation Technology. Is one of the other programs available, software available. COMSOL, others that I can't remember now. ADS has also something similar integrated into it. If you go to ADS and you want to simulate your circuit, you've designed a nice circuit, you lay it out. So you go from your schematic description to a layout description, and then you want to simulate that layout description because you have bends in your circuit, and you're having fear that, okay, if I have a certain U band, how much of the electromagnetic wave will actually go through the U band and see the electrical length, and how much will couple over it and just see part of the conductor. So you have a similar simulator there, which is not 3D but 2D, and it's called Gott, das habe ich vergessen. Well, it's a very equivalent simulator in Momentum. Yes, you're right. Oh. Momentum. Momentum works on similar principles, but instead of having a 3D object defined, you define a substrate definition, and it uses that substrate definition in more of a sheet. It simulates sheets and doesn't simulate really 3D objects. I think with newer versions of ADS, they've changed that. With ADS 2015, it was that it still did the sheet thing. With CST, you can do a full object, and basically you have here, you can start a new project, and the project, it has a project template, so it can help you into moving you in the direction where you want to go to, and you can have temperature solvers, you can have integral solvers, you can have time solvers, frequency solvers. Usually we are operating in the microwave and RF and optical device side, and then you can choose between the if you want radar cross section, if you want optical applications, circuit components, and so forth. For example, if you go with an antenna, it will ask you what type of antenna it is, what is planar, wire antenna, phased array, 5G millimeter wave antenna, and it will try to adjust the settings as you require them. For example, what is the size, and what is the starting frequency, what is the ending frequency, what kind of monitors do you want to have, E fields or whatever, and it just generates a plain starting space. But we don't need that. We have already something here. So it would, if I were to hide everything, this is going a bit slow because of it would generate something like this. So it gives you a plane, it gives you a working space, a main coordinate system, and the coordinate system that you define. And then you have it here. You can define a local coordinate system if you want or not. And you have something like that. Also, this port is not even there. Let's start with this empty space. Here in this empty space, you have some definitions. You have definitions of frequency. I have it here from 0.1 gigahertz to 800 gigahertz. My antenna that I design is currently focused at 400 gigahertz. You have a certain background definition. You define what kind of background, how much space you want to give it. You have boundaries then, like what are the boundaries? Are they magnetic, electric? Are they open air boundaries? Open at space is usually the case. And then you have an electric boundary in somewhere, or a magnetic boundary if you have a symmetric. If you have a symmetric device, you can add a magnetic boundary, and then you basically save yourself half of the simulation time because it's flipped, it mirrors your results. In order to start, you need the materials. Here they're defined. You define these materials from a library internally, or you can define the materials however you want. Materials like air, diamond in this case, vacuum, quartz, there's conductors here, which is gold, alloy, nickel, chrome, whatever is required in our process. Now, having these definitions, you can then start to define the components, and the components can be defined by modeling, and you can start defining either squares or spherical components, or it is not as easy as just starting to draw, like, hey, I want to draw this and that. You have to work a lot with constraint objects like squares, circles, and so forth. What you do more advanced in time is that you have a layout, and then you use software to convert that layout from a 2D to a 3D model by really discretizing each part of that layout into smaller quadrants. And then you add all these quadrants together, because this works well with if you have defined shapes, and then you merge all those shapes together and you have a 3D model. Now, what I had here was also this antenna that I showed you. So this antenna, what does it consist of? Well, it consists of the substrate. The substrate in this case is divide only these chunks, but if they touch, they are basically one combined. So the substrate here, 140. This is the GaAs substrate. This was a chip. This was an antenna that was processed on an MM chip, so an MM indium gallium arsenide process. This is a GaAs substrate. It has a metal plane on the side, on the back side. You can see it here, and then it has the substrate, and then it has the back end of line. So the many layers of PCB metal, PCB silicon nitride, PCB metal, and so forth. And we're designing an antenna on the top metal side. So this is how you design modern antennas in modern IC circuits. You're designing this antenna. You have a certain size. You're starting with the mathematical part, which is you're defining, okay, I need a certain edge. I have a certain formula for microstrip antennas. And I can define, okay, I need this edge length because I have this size of substrate, that size of dielectric constant, and this is approximately the size that I need. So you start to design this. You define a port. A port in case of CST is just a waveguide port that is that you point into a certain metal into it. You have to have like a uniform transition, and then what it does is it excites a wave, and the wave looks a bit like this. Port modes here, port 1, E wave, for example. The program is very slow for everything. Yeah, that's a VIA. Yeah. VIAs. You can put the VIAs wherever you, but that's the VIAs in that case, yeah. And the VIAs play a bit of a role as well in the way that it radiates, but that's besides the point. I want to show you how the modes, the excitation modes looks like for the port, because you have a structure like here. You define a port, and in that port, then you define you try to define the mode that you want to work at. And we had the microstrip line, which means that we want to see a microstrip line mode. So if I hopefully show all objects. Yeah, so you can see here, here's the conductor, the top conductor, and the ground plane is the metal plane here downwards. See how the waves are propagating, and they propagate in the manner how you'd expect from a microstrip line mode, which means there's the majority of the waves. The majority of the field is concentrated between the conductor and the ground plane, and then you have the fringing fields which are on the side, which propagate. If you don't have this kind of conductor, if you have a coplanar wave, it obviously will look different. But what is important when you use this kind of software is that you look whether you're able to excite the correct mode of correct mode of the wave that travels through. If it is a microstrip line that you're trying to excite, then you want to have a microstrip line mode. If it's a coplanar line, then you need a coplanar mode, and not something in between. Obviously, you can visualize this in contours as well, and like increase the range so that you see it better. See, this is basically what is being excited right now into our antenna. And we use this port to define our one-port device, but we run through simulations, as I said, through these EM simulations, and each iteration you see the results, and then you adjust in your parameterized components. Now, in order to be able to, like, as I said, to increase, because these sizes are very small, because these things are very small, I don't know, the edges, what is it? It's 74 micrometers. The directivity of these antennas is very low. In order to increase the directivity of these antennas, people have come up with solutions, other solutions. What can be done? What can be done inside here? There's also things that are being done inside here, for example, below the antenna. If we move here, always a little bit of delay. So if you move below the antenna, this is the part below. I don't know if you can see it, but if you move below the antenna, there's obviously structuring being done with array types of antennas underneath to help the radiation to increase again the gain of this antenna. But below, working with what is being done below, people have started to imagine, oh, okay, what can be done if I do something upwards in case? And upwards in the case is if you do something like add a dielectric resonator. So this kind of block. So block which is excited then with the energy coming from the antenna, and this block radiates over the frequency. And this needs an interrupt. The waves need an interrupt in order to be dissipated. And we can maybe see that in a good example with here. Yes, very good. 400 gigahertz. We'll hopefully be able to see how the visualize the EM waves. Let's just see if everything is going right with the recording. Yeah, it's recording still. Very good. So, what do we have here? No. You see? So from the, and the peak is in the middle. From the middle, basically where the patch is, this object starts to, the whole resonator starts to resonate and to generate a certain, to first of all direct the radiation from the antenna below, and to radiate a certain pattern. And how that pattern looks like, we can see in the far field demonstration. So from all this, we come to this kind of radiation. So this is what the antenna is doing. It is radiating the signal with a directivity, I think in this case, let me see. The directivity of 9.6 dBi with respect to an isotropic radiator. So there's around 10 dBi of directivity, but the directivity doesn't take the loss in the efficiency of the size. And you can see that the actual gain, or the realized gain, I would say more, if the realized gain takes also the losses in the conductor, the actual realized gain is here upwards is 7.5 instead of 10 dBi. But again, with dBi, with respect to an isotropic radiator. So this is how the antenna then radiates. If it didn't have this quartz, it would have only 2 dBi. But 10 dBi at 400 gigahertz is maybe 20 centimeters reach. So after 20 centimeters, your wave will have, first of all, you have anyway not enough power that you drive through the free space there. And second of all, you'll have a signal which will be in the range of minus 80 dBm if you receive it then after 20 or 30 centimeters. So what nowadays is being done basically is the integration of lenses with these kind of solutions. And so lenses are integrated. And what is a lens? The lens is what we see here. So it is a dielectric, it's basically, a lens is technically a parabolic reflector, but a parabolic reflector constructed into a dielectric material shaped such that it can be positioned above a focal point, above a device which incites a certain EM wave which sits in the focus and drives through the and what in this case it does is that the whole the radiated waves that come through here, they basically are penetrating this way, penetrating in the middle, and so forth. And the ones that are penetrating in the middle, in order to here to have a plane wave, this is trying to make from a semi-focused signal into a plane wave signal. The ones that are radiated here, in order to have the same time that they reach it for the wave to be able, whatever enters here, maybe I'll see it like that. Maybe we see it in a port E fields. Yes, very good. 400. Sehr gut. Let's see. Fields on the plane. And then we'll talk about azimuth, and yes, that's a good. Oh. I hope it doesn't crash on us. It did crash on us. Well, we'll open it again. Okay, I can still do at least something. Let's see. Let's give it some time. Before that goes. So technically it's something like this. So how it would look like. You have your source, and then you would like here to have the waves that propagate out here to be plane. In order to achieve that, you have an antenna, and a lens. And what this lens does is this. The waves that propagate through the middle have to have the longest path, technically. So you have a certain epsilon. What does the certain epsilon do in the dielectric constant? In the dielectric constant in this material, it delays the wave propagation. Dielectric constant is defined as the tendency of refusing rate of change of an electric field, which means that you're delaying the propagation time of the waves that enter here. You're delaying them all equally, obviously, but the waves that enter here and propagate here out, they see the least amount of length, whereas here in the middle, they see the most amount of length. But what you want to achieve is that through this shape, you want to achieve that all these lenses, when all these EM waves, when they exit the lens edge, that most of them meet at the same phase and are able to be radiated out as a plane wave. What the lens does, and the effect of that, you can see there's a main focal point and the second focal point. So it gets in here the high energy intensity. Then the far field. The far field from an antenna that was this was the far field. So you can imagine in size it's something like that. The comparison becomes this. Because that antenna that we had there is right here. Oops. Here you see it. This is the source at the focal point of this thing. This is the effect that it does in terms of the gain. And then you have, if you go to the realized gain, you have something that was operating with something that was operating in the range of 7.5 dBi to something that's operating in the range of 23.5 dBi. You increase gain. What you do is an antenna is no active device. It's not producing energy or it's not boosting your energy. You're losing energy anyway in the moment. But what it does is focuses better. And the more it focuses, the less energy is being spread everywhere around. The more energy is directed at a certain point, which you then can reach. If you have, the more focusing you have. If you have a widespread radiator, I wouldn't be. If I'm a amplifier and I have 3 dBm output power, and I'm putting an antenna on it that spreads all in the 180 degrees shoots, I won't be able to reach any of you. But if I have the same amplifier and an antenna that focuses the beam, the losses are the same because the antenna just induces losses. It doesn't generate power. It's a passive device. But still, the whole amount of energy that has been all over there, if you integrate it, will be all the same. But because of the fact that it's directed, I will be able to reach one of you guys from where I'm standing here, hypothetically. This is the effect of the lens, and this is usually what's most research now is some type of lens integrated in some type of horn, some type of antenna as on chip integrated with a packaging that has a lens, some type of array that uses a lens configuration, that uses a metastructure configuration to increase the directivity, the gain. All the research in terms of antenna, in terms of high frequency, is in this department, in this area, in this spreading in this area. Where here you can see the components, what you said, the phi and the theta. The theta was the elevation. So it shows you which cut. For example, we would go to a polar plot of this 3D view, if it allows us to view a polar plot, because I think that sometimes the data set is too large for it to handle. You learn it with experience, I guess. Maybe we'll be able to see. If not, we'll look at it at the other one. So let's see here. Here we also have the parameters. You have an E vector, you have an H vector, you have the propagation theta, the propagation direction, you have a theta, and you have a phi. So the theta was again where my main lobe is directed, and the phi was the azimuth was to show me in which direction am I looking at. I'm making this cut, but in which direction am I making this cut? Am I making this cut here? Am I making this cut here? Am I making this cut here? And so forth. If you want to make this cut and this cut, you will have to have a 90-degree azimuth, you make a cut. You make a 270-degree azimuth, you make a cut. And this will hopefully be able to see in the 1D, in the polar plot view. And yeah, I mean, the sizing and everything, you can change how you're going. And what is this? This is saying that our phi is 0, and our theta is being swung the full circle. So from 0 to 180, from 0 to 180. And why is it not going 0, 30, 0, minus 30? Is because this is saying in one side you have phi 0, and on the other side you have phi 180. So one you're having phi 0 here, so you're doing this. I'm taking this part, and then I'm doing 180, and I'm again doing 0 to 180. So I'm doing this axis, but with two of these movements. So the first movement is this, you analyze this part of the circuit, and then you move 180 degrees, and you analyze this part of the circuit. And that is to define something that is in 3D, this, to be able to map it in 2D so that you can visualize the information. In CST, it's very easy to have a 3D view. It's very easy. But when you measure your thing, it's not very easy, because measuring these devices is very complicated. It is often enough very annoying to measure these things. And I'll show you maybe some example of that. Actually,
This is a robotic arm, which then lightly shifts around in the horn. So how is it characterized? This is a receiver at 400 gigahertz. It has a horn. And as I said, horns are nowadays used in labs to characterize other antennas. And then you have the antenna, the developed one, which is on a chip, and the chip is put on a PCB board or on a packaging, because you can't just take a microchip sizes of the chip and just be like, oh yeah, I'm taking. Oh, maybe I should come here. You can't just take a chip and be like, okay, I'll plug it in and radiating. The chip needs some packaging, the chip needs some environment, a PCB where it's getting all the DC voltage that it needs, where it's getting all the RF signals that it needs. So you have a bigger packaging, a bigger PCB, but the microstrip line, the microchip and the antenna are minuscule. And they're mounted on this device as a KUKA robotic arm, which in industry you can use for anything, but here you can also use to just make these movements for characterizing the antennas. And what the problem is that you're characterizing this thing, which has to be exact in the movement that it does, and then, I mean, you have the receiver, or what is everything doing? First of all, you have a spectrum analyzer. You have two function generators. One generates the local oscillator or the local signal for the board. One generates the local signal for the receiver. The receiver has an IF cable which goes out into the spectrum analyzer. Usually the signal that is transmitted from one to the other has a delta. It's around whatever you put the delta, if 1 megahertz, 100 megahertz, depending on the device. So the delta allows you to actually find the signal that is then, the signal is like, it is a baseband. From baseband is multiplied up to 400. It is received at 400, comma 1. And that one is mixed down to the baseband again. And here you can have the delta, which you can see then the signal that you received. You need the delta to be able to down convert to a baseband signal. And these are just DC power supplies for all the components. The distance here is 15 centimeters, maybe. So to be in the far field of these things, because they're so small, it's very easy to be. And what did I want to say? Yes, the problem here is you have to characterize this thing exactly, and whether you use a turntable, whether you use a robotic hand as this, as whatever, to be able to look at it in 3D like we looked at it in CST. To look at this, you will have to go through multiple iteration times. It takes a huge amount of time to be. That's why what you do is you characterize this plane and this plane. So you characterize this and you characterize this from the antenna. And all in between you assume that will be converging with the simulation. If the simulation is converging with what you measure. To get this kind of view, it's very difficult. That's why these parameters, theta and whatever, are very important. Because if you measure only this thing and only this thing, you have to be very exact when you tell the customer or your professor or whomever, what have you measured there? Because this kind of cut can be from anywhere. It can be from this side, it can be from this side, from this side. Only you as the person who measured it knows it because you've measured it yourself. But the person who evaluates it can be like, oh, I don't know what that means. So these phi and theta are very important parameters to say, okay, what I measured was, I measured from here to down here on this side, and then I shifted myself 180 degrees and I measured again from top to bottom. And so I had this kind of cut in this case. Yes. So CST, it generates information, it generates far fields, it generates and here, for example, an input matching or input reflection coefficients, not an input matching, sorry. So you can see the reflection coefficients, how well you're matched. You're interested in from 340 to 420, and then you notice my antenna is working very well in between. So usually it's a standard definition that you say, okay, it's working well from the point where only 10% of the power that you've pushed in, where only 10% or lower are being reflected back, where 90% of the power is going through. And so then you have it, for example, starting here, 345, until around here, around 425, so around 90 gigahertz of operating frequency, and around 90 gigahertz, your far field patterns, so what you radiate, should be consistent. They should be all, der will nicht. Ah, nee, das was falsch, sorry. So your patterns should be all looking in the same direction. Okay. Their patterns should be more or less similar, because you want your antenna, if you purchase an antenna, you want the antenna to be more or less the same across the operating bandwidth, and not, somewhere different and then somewhere completely bad. So it should be more or less the same. So here you see, it's operating wrongly here. Maybe you start to use the antenna only at 370, 380, 390, 400, 410, 420, 430, and then again you see, it's already making some weird things. So there's a play between how good you're matched and how good you're radiating out. Yeah, I think this is enough. And I think this was also enough. And I think we can move on. So we saw modern antennas are designed differently nowadays. You have a certain result, and then you can compare your results as a simulation. Basically, this is a plotting of the measurement to the simulation. Simulation is with dotted, measurement is with not dotted, and you see that the far field really aligns quite well. The S parameters are also quite good alignment. At least you know the region where it's operating at. The shape is quite good. The how well the match is quite well predicted by CST. So in modern days, EM simulation tools are the key. Now, what we said before, we have these tiny antennas and we want to make a huge array. And how do we make a huge array? Well, we use the property that a huge array of an antennas is basically, if you take the function of the system, and if you take one radiation characteristic, then you can just multiply that function of the system with one radiation characteristic, and you will know how the whole array will behave. In that principle, we can design from one small tiny thing, we can design a huge array, because we can just use this property of multiplication. I mean, there's complications obviously otherwise, but for example, how does that work? Well, if I go to 400 again here, and I go to array factor, and then this array factor, I activate the array factor, and my frequency is 400 gigahertz. That's a wavelength of 705 microns. So what is my half, lambda half? It's around 300 and something microns, so around 400 microns. So if I make this 400 microns to each other, and I say, well, I want a 6x6 array. So in X and Y dimension, I want 6x6. So I have really the information that I have is only the far field patterns of one antenna and the characteristics of the system. What are the characteristics of the system? The spacing of the elements and how many elements are there and in which direction are these elements. And then I click OK. And then from one simulation, I can have a pattern. I can have a pattern which looks like this. And you see this pattern is starting to look a bit like this. And if I make even more elements, the gain will also increase. You see? So the far field pattern is starting to look a lot more like what the lens does. So the lens and the Cassegrain array antennas that we saw in the beginning for space observation, that can all be not simplified, can all be replaced by using arrays, by using multiple arrays. And how you calculate beforehand, before making these arrays, is that you use this the multiplication principle, in that the system, the array will behave like the unitary behavior of a cell multiplied by the system's parameters. And the parameters are the spreading, the direction of the spreading, and so forth. Now we saw that this is really turning into that, and that we see then nowadays as well, in that instead of for observations of in in New Mexico, for observations of black body radiations that are coming from space that are so minuscule, in order to be able to even recognize that, you would have to make a really gigantic array, gigantic aperture. And to make a gigantic array, to the amount of metal that would have to be moved around or whatever, that's insane. So instead of that, you make an array. Here you have basically, with this kind of construction, you basically have an aperture which spans the complete thing. So you imagine if you had here a completely huge parabola. The similar thing is also here. For example, the exact same principle, where you're reducing the amount, you're spanning an aperture, a virtual aperture with that is exactly the same as the real antenna, with these components in array setup. This is similar for arrays are used in space applications, in satellites and so forth, because of the signal, the reduced signal strength. You would like to increase the directivity. In order to increase the directivity, you have these multiple antennas sources. Another application of these apertures, spanning an aperture, is, for example, ZA, synthetic aperture radar. What does synthetic aperture radar do? Well, synthetic aperture radar, in order to have a high resolution image, you have to have a high directivity and high selectivity, which means a very large antenna. To have this very large antenna, in order to make radar images, what is a radar image? You send a certain energy forward, you get a certain reflection. That reflection, you take the phase and you take the amplitude, and you can able to construct a mapping, and then you call it an image, this mapping of the amplitude and the phase. You would have to have a huge device, and what is going to carry that huge device up in the air? So what researchers do, and what industry now does, but researchers especially, is that they use synthetic aperture radar, and the synthetic aperture radar makes use of the principle that you can instead of having multiple, even having multiple, you can span this. So you can span the aperture by having multiple antenna elements, but you can also have one antenna element which is always moving in a defined trajectory, and you always know where the reference is, what your distance to that reference is. So with a laser, you're measuring always the distance. It's very important to always know the distance, and you're making this image, you're moving your device in a controlled manner, always controlled, moving, controlled speed. And for all of that, you're making chunks, and all these chunks, the information that you gather, you're superimposing it and basically expanding your aperture. And what you do with that is that you gain a far higher range resolution, a far higher lateral resolution. And you can see an image done by a radar which doesn't use synthetic aperture, which doesn't have the synthetic aperture as in ZA, isn't even capable of discerning the detail that is in the. This is the same image, but one done with normal radar principles and one done with synthetic aperture radar, which basically emulates as having a gigantic antenna transmitting and receiving the information. Another point of communication in modern world, not only in radar, but you're also making use of communication. Why you want these multiple antennas and multiple components? Why you're going always smaller and smaller, making multiple? You're going smaller because you want to go higher in frequency. As we know, smaller devices, smaller gate lengths produce signals that are higher in frequency. Smaller gate lengths, smaller processes, also the antennas become smaller. You're transmitting at 400, 360 gigahertz, whatever the case. Now, beyond having this numerical aperture, which you want gain and whatever, you want these small devices because it's easy to parallelize these small devices, easy to make arrays of these small devices. And what's easy to make of them is to have a row of transmitters and a row of receivers, and the transmitters to turn them on one by one. So multiplexing I turn one channel on, the rest of the channels are off. I turn that channel off, I turn channel 2 on, the rest of the channels are off. I turn that off and then turn channel 3 on, the rest of them are off, and so forth, whilst my receiver is always on. And what happens? If you have 5 transmitters and you have 5 receivers, then for every time you turn on the transmitter and the receivers are on, you'll be able to superimpose whatever you transmit over these receivers. So you'll always have once you've turned all the transmitters on and all the receivers sequentially, and all the receivers are always on, you will have from a 5 transmitter to a 5 receiver array, you will build a 5 by 5 matrix. So you will span a numerical aperture which is equivalent to a 5 by 5 matrix. And by 5 by 5 matrix, what can you do is that by shifting the phases of these components, you can direct the beam. So I can look at you, I can look at you, I can look at you. I can direct the amount where my beam is going. And that is only capable because we're working with these small devices which are easy to process on a semiconductor process. We're able to parallelize them on our chip, and then we're able to steer the phases because we have active components that are steering the phase. We have phase shifters steering each of the components, steering the phases. And the phases, what they do when they're steered is that they steer the beam direction. And that is what 5G is important or interested in, and 6G and any other G will be interested in, is that to direct the amount of Leistung. So you have one sender which is sending always in a dispersed manner in a large cone, but then you will have another smaller sender which then says, oh, this guy wants to watch Twitch at 4K, so I'm going to send all the information to him. Well, these guys are just browsing the web and looking at 9gag or looking at Reddit or whatever. So then I'll move my beam wherever I need to move it. A similar process as in listening to things. We have 2 ears. We're able to echolocate things without having to move our heads because of the positioning of the beam. That's what you do with the positioning of these arrays. In order to span this MIMO array, this virtual array of 5 by 5 or 10 by 10, whatever, you have the positioning of the 10 transmitters, the positioning of 10 receivers, and you turn on each one sequentially, and with your ears you always listen. So you have that crack here, that crack there, we're listening always with your ears, but if the cracks come separately at time, you'll be able to identify and say, oh, I know that the crack came there because I saw the phase difference. You hear this first, and you because of the 2 ears, we're able to identify a difference in where if we have 2 reference sounds. And in similar thing happens also in antennas and so forth. Well, that was actually it. In the next section, we'll go to active components. That was it for the antenna part. Yeah, if you have any questions, otherwise, this is an introductory part. What is important to remember, this for the exam, it's just good to know the main parameters of the antenna, main principles, for example, directivity, the gain. It is good to know how is the far field plot, where is it plotted, how, and what does the horizontal and the vertical lane show, what are side lobes, why do you want them to have low, how would one, with respect to what would one characterize an antenna? I mean, you have always, I said always you have to have, you're adding dBi, why are you adding dBi? Because you're doing it with respect to an isotropic radiator and so forth. So these are the simpler, yeah. But yeah, just look through it and don't worry about too much. Yeah, I think I would conclude the recording, and I would thank you very much for